Intro to Logic. Hypotheses and conclusions. Most of you are probably familiar with these terms, but let's break them down. Enter the hypothesis. A hypothesis in a logical statement differs from a scientific hypothesis, which gives an explanation. A logical statement hypothesis is a statement that tells you the expectation of what will happen. Example, it's raining or the dog is hungry. That might not make sense in that example. Bear with me a minute. A conclusion is the result or consequence in a conditional statement. It is what results from the hypothesis. Examples to the above: the ground is wet, or the dog begs for food. Together, a hypothesis and a conclusion bind together and form a statement that gives a starting condition and then gives a result based on that starting condition. Full examples: if it is raining, then the ground is wet, and if the dog is hungry, then the dog begs for food.
Mathematics likes to make generalizations because it can talk about a lot of things at once rather than talking about one single thing at a time. When there are an infinite number of triangles, talking about one and one only is not particularly effective. So, generalizations are made to be broad for the sake of the number of things that can be covered by this broadness. Sometimes, however, generalizations are too expansive, and this leads to the need for a counterexample, which demonstrates a generalization is too broad.
Counterexamples. As mentioned above, not all generalizations are true for all cases they talk about. Math tries to make these broad sweeping statements that are true if other things are known to be true. Sometimes there are examples that make generalizations false. A way to show they are false is providing a counterexample. Enter the counterexample. A generalization: if a bird has wings, then it can fly. But if you've ever heard of an ostrich, you know this isn't true. But here are some other examples in case you weren't convinced. There's the kiwi, there's the dodo, there are penguins, and so on and so forth. Conditionals. Enter conditionals. We already encountered conditionals earlier in the form of the hypothesis and conclusion couplings seen at the beginning. Conditional statements follow a form of if A, then B. Side note, if you have ever done any coding before, this will look and sound familiar. Many of you haven't, and to those who haven't, treat it as a claim that shows a cause and effect. Conditionals can come in multiple different forms, but here are a couple. If the dog is scratching at the back door, then it needs to relieve itself. Or, in more mathematical form, if a number of your choice is greater than 7, then your choice was greater than 3. With math notation, if C greater than 7, then C greater than 3.
Negations. There are things in math called operators. Operators are symbols that indicate when a certain operation should be performed. That is to say, when a certain action or manipulation needs to be performed on a number, a variable, or some other mathematical thing. There is an operator called a not operator, which looks like this. This takes an initial logic value, whether it was true or false, and reverses it. An example: if you are breathing, then you are alive. So, say you are breathing, then the hypothesis is true. Well, not breathing negates the truth of breathing being true, which means you are not breathing. That is how the operator works on statements. Negation can be performed on the conclusion of the conditional statement too, which means a conclusion that is true now becomes false, so a conclusion living now becomes not living. Say we're looking at a variable named age, and age is greater than or equal to 18. This is used in the statement: if your age is greater than or equal to 18, then you can vote. Well, if we take the age that is greater than or equal to 18 and we use a negation operator on it, we find out that it goes from being the upper diagram, which shows ages 18 or older, and it ends up giving us the lower diagram. As you can see, the line to the right is going to end up being those ages that are older than 18, and then there's the dot, which is actually 18 itself. If you look at the lower diagram, you'll see that there's a hole there, which means that 18 is not included, and the arrow goes in the leftwards direction, which implies that it's only ages that are less than 18. So for the overall statement of if your age is greater than or equal to 18, then you can vote, And if we negate the whole statement, we are left with, if your age is younger than 18, then you cannot vote.
Inverse. Enter inverse. An inverse is when a negation is used over an entire conditional statement, not applied to if A then B becomes if not A, then not B. This means we reverse the truth value of each part of the conditional statement. That means we made trues false and falses true for the A and B. The word inverse comes from in plus verse. In means not in this case, and verse means turning or flip. So inverse means flipping negative. Converse. Converse is when you take a conditional statement, if A, then B, and turn it into if B, then A. Verse was defined above, but con comes from com, which is a Latin prefix, and it means with. So, this means turning with, and refers to the role flipping of A and B, and the fact they keep the same sign together. Contrapositive. Contrapositive has an odd name. Before talking about it, let's break down the meaning. It sounds like contra plus positive, which would suggest it means against the positive, but it derives its name from a different term. It evolved from contraposition, which means against position, which can be thought of as against and positioning. Inverse or the inversion is the against part of the idea, and converse is the positioning or repositioning of terms. This can take a statement, if A, then B, and turn it into, if not B, then not A. That is the form of the contrapositive. The and or operators, logical meanings. When you have two sets or groups of things and you use the and operator, it takes the two groups you have and creates a subgroup that contains only the items common to both groups. In a logic context, it says that the collective is true only if both logical statements are true. So here's an example. In the set context, say we have two sets, A and B. A contains 1, 2, and 3, and B contains 3, 4, and 5. So, if we perform the AND operation on the sets A and B only gives us 3, because 3 is the only common element to both of them. In a logical setting, A and B says that the whole statement is true only if A and B are both true. So it is true if A and B are both true. The forms are similar, but the curved bend is meant to show ands for groupings / sets, and the sharp upside down V is the logical and that serves a similar purpose.
The OR operator combines two sets into a collective group that contains all the unique items contained within each of the individual sets. If it's a logical OR, it means only one part of the conditional statement needs to be true at a time for the statement as a whole to be true. Here's an example. Say you have a set A and a set B. Set A contains the names Will, Martha, Maria, and John, and set B contains Maria, John, and Jane. Then the union, or the A or B, of the sets A and B will end up producing a named set of Will, Martha, Maria, John, and Jane. In the logical setting, A, V, B is A or B, and it is true if A or B are true. The V looks like the upside down V that we saw for the logical AND earlier, and the U is the equivalent of the upside down U for the AND we saw earlier, but in this case, both stand for the OR operator.
Biconditionals.
A biconditional statement is a statement that shows a logical statement is true forwards and backwards. This means it is true forwards and its converse is true, since it is a matter of position reversal between A and B. Key indicative phrasing for this would be if and only if in a written statement. In a symbolic representation, a double arrow going both left and right indicates this biconditionality. Example, if your heart is not beating, then you are dead, and if you are dead, your heart isn't beating. Written another way, your heart is not beating if and only if you are dead. Truth tables are tables that consider when logical variables are either true or false. The tables tend to combine them into more complex logical statements and expressions, and they consider the outcomes when one truth value between all the logic variables changes from row to row. Note, in logical statements, A is called the antecedent and B is called the consequent. If you want to refer to them both by different names, the A portion is the if clause and the B portion is the then clause. Here is an example. If you look here at this table, we have two logic variables, P and Q, and the composite expression they make is P and Q. In the first row, both P and Q are true. In the first row, both P and Q are true. In the second row, P is false, Q remains true, and it oscillates back and forth as you can see in the diagram. With that in mind, only the first one of those four outcomes is true when you make the composite expression P and Q. This is because the AND operator, as mentioned earlier, only ends up acting and behaving true when you have both of the logical variables involved in it being true on their own. Now, there's something about the rows I want to make clear, because only one variable can change at a time. All single lone logical variables should evaluate to true or false initially. They change in groups with each other. The best way to put it may be to treat every logic variable as having one of two forms, true or false, as stated earlier. For each variable introduced, you increase your number of combinations by 2, or permutations by 2. The form takes on 2k many permutations, which also matches the number of rows. So k equals 1 produces 2 to the 1, which is equivalent to 2 rows. For k equals 2, you have 2 to the power 2, which is equivalent to 4 rows. And there is an example we will get to later that happens to end up having 3 variables, and thus 2 to the third power would imply that there need to be 8 rows. For the sake of an aid of whatnot of understanding the table we just presented to you, I ended up coming up with something which I like to call a logic tree. This is a representative pathway that shows you the different options you can take within a tree, which when taken together tells you the different permutations that you can have that appear within the tree. It explains to you why, when you look at it, the table manifests the values in the way that it does. This is a 2-variable tree, and we have a first split chain of 2, and then each one of the queues below has its own split chain of 2. You take the given values from each P and each Q along the way to go and find the different number of permutations they can have for the different truth values, i.e. true and true, or true and false, or false and true, or false and false. Practice on truth tables will be something I will deal with in a small future video, and in dealing with that, we will talk about this 3-variable tree, and I will provide you with the explanation for why it works the way it does, and then we will also go into solving a couple of practice problems so you may gain some experience with it and find these things more understandable to you if this is in fact the first time you're encountering them. So let's give this truth table a look for a moment. I'm going to give an example to contextualize it. This will clarify a confusing part of the table you'll find in the third line where A is false but B is true. So, say we have an A. A stands for the city of Miami and B stands for Florida. Well, if you're in Miami, then you are in Florida. If A is true and B is true, then in this case, A implies B. If you are in Miami but somehow not in Florida, then that makes no sense. And obviously, if it's true that you're in Miami, but false that you're in Florida, then implying that you're in Miami implies that Miami is in Florida would be false. Skipping to line 4, if you are not in Miami, then you are not in Florida. This can make sense. You could be in London. Now, back to line 3, if you are not in Miami, then you are in Florida. And this is true. Look at it this way. Just because you are not in Miami doesn't mean you can't be in Florida. So, A can be false and B can be true. This does not mean the collective statement that being in Miami implies you are in Florida is any less true, just because you're somewhere else in Florida. For all you know,
You could be in Tallahassee.
Well, that concludes the video. I want to say thank you for watching and for tuning in. This took a while to get this one up after the introduction video because I did not realize just how much I'd have to edit it along the way. It was a lot more than I had in mind initially. This is also the first real video I've ever done on my own, so there is that too. And in the sake of trying to be thorough, making sure sources are cited and so on when it was appropriate was also something that took a little bit of time. So thank you for paying attention and for bearing through this labor of love. And I hope to see you in the next one. Thank you. Goodbye.